So today we're looking at chapter 9I, weighted graphs, networks and the shortest path problem. So the first thing we're looking at is the weighted graph. Now, a weighted graph is when you have numbers associated with an edge. Okay, so the numbers, they're called weights, so the edge has a weight to it, it has something assigned to it, and it usually represents quantities, so for example, time, cost and distance. Okay, so with, and very important, let's do a different colour, a weighted graph is called a network. Okay, so I guess this is where the whole topic comes in, so graphs and networks. Okay. A network is when a graph is weighted. Okay, so when edges have a number associated to them. So for this one, we've got a graph. So a graph, see how it's got all the vertices labelled and it's got edges connecting them all, but the edges, we don't actually know the distance between the towns. Whereas with a network, okay, we've got all of our towns here, and we've also, each edge is weighted because it has a number here. I might do a different colour. Okay, all of these numbers here represent the distance between towns in kilometres. Okay, so there will always be like a bit of an explanation of what the number means. You've always got to make sure you know, or you've allocated a quantity to them. So yeah, we've got, for example, between town A and B, so we're looking at this edge here, the distance is 7, so it's 7 kilometres, which we can see there. For this one, if we go from town E to C to D, okay, so we've got town, interesting, oh yeah, town E to C to D. We've obviously got 4 here, plus 5, and then plus 6. So that's where you get the 9 plus 6, which equals 17. So 17 kilometres. So this is what we call a weighted graph. Which is a network. Okay, where the edges have numbers associated to it. So that's that first part. Hopefully straightforward. And then one last thing in this chapter, what we look at is, actually I'll get the highlighter back out. We're looking at the shortest path problem. So you're going to be getting questions that will ask you to find the shortest path. Okay, so the shortest distance. Sometimes we look at costs or something. So yeah, we're determining the shortest distance or time or cost. That's usually what the numbers are about, to move around a network. Now, the method is important, okay? You need to examine every possible path. The most direct route visually may not always be the shortest, okay? So just quickly, down in this example, you've got a really short looking edge here, but it's actually 7, okay? Whereas this big edge is 5. So you would expect the bigger edge to be 7, but it's not. So you need to make sure you're not just looking at the actual physical length of it. You need to be looking at the numbers. That's why it's important to examine every possible path. And then you find the sum of the paths. So you add up all your paths and write the solution in the format below, which looks like this. Okay, you need to show us all the different routes you've done to see which one is the shortest. So for this one, we're trying to find the shortest route between town C and town F. Okay, so our first route we can look at is from C, D, E and F. That goes from C to F. Okay, we've got 6, 9 and 7, which is 22 kilometres. So that's one route we could take. We could also take the route C, B, E, F. So we need to add 5 plus 4 plus 7, which would be 16. And we've also got the root if we go from C to B to A to F. That would also get us from C to F, where we've got 5, 7, and 6, which would give us 18. Okay, so from looking at that, we can see that the shortest path is CBEF. So yeah, it's very important to examine every possible path, and visually you can't tell what's the shortest. Okay, you actually need to be adding up the numbers, finding the sum. And that's it. We can work